I welcome you once again to this course on microscale transport process. In the last class, we were discussing about deposition on silicon and glass. What we had so far covered is a technique called photolithography, by which silicon substrate can be etched in selected locations, and that process is utilized to make channels of certain depth on the substrate. What I pointed out is the next thing you need to do to this substrate is you need to make deposits on the channel wall, which will constitute electrode, catalyst, thermal or electrical insulation, absorbent, optical elements on the wall of the channel. So, for various reasons you need to make some deposition on the channel wall, and once that is done, then you are supposed to close the channel by putting another lid on top of it and seal the channel. And once you make some interconnects, that means once you make some ports through which you can connect a pump or you can connect some other external source, then this microstructure device is all done. So, deposition on silicon and glass, here I already mentioned what all reasons for which deposition needs to be done. There are two types of depositions possible. One is physical vapor deposition, where certain species from the holding gas is adsorbed on the surface of the target, and there are two types. One is thermal evaporation and other is sputtering. And in chemical vapor deposition, certain species from the holding gas reacts with the target, forming compounds that are chemically bonded to the target. So, these are the two forms of deposition that is commonly pursued, and in the last class I pointed out that there are certain benefits to get this deposition done from the gas phase. That is why we are talking about two vapor deposition process, and we are not going through the route of precipitation from a liquid phase, though that is a very viable technique to make a deposition on the channel wall, precipitation of certain material on the channel wall. However, since a gas phase diffusivity is much higher, you can expect a better crystalline structure when you deposit it from the vapor phase. Now, there is this I said there are physical vapor deposition is of two types, one is thermal evaporation and the other is sputtering. In thermal evaporation, what you do is, first material to be deposited faces the target in a container. Then the high temperature ensures sublimation of material, and then low pressure ensures avoidance of unwanted parasite deposition of molecules present in the chamber, and then deposit rate is given here. It is simple to implement and good for metal deposit. What you do in this thermal evaporation process is that you take a chamber, you have some heating arrangement. So, this is practically a furnace. So, you have the heating arrangement, and you have, suppose this is the substrate which needs to be, this is the substrate and a part of this substrate needs to be deposited. So, you leave this part exposed, another part unexposed, and then you keep this solid material that you need to deposit, you keep this solid material next door, maybe at an angle, and then you heat this solid material. So, this solid material undergoes sublimation. So, it goes to the gas phase, and there is a gradient in temperature. Maybe the heating is done on this side, maybe the heating is done on this side. So, heat is supplied here and this part is cooled. So, there is a gradient in temperature. So, as this sublimated material, so which is basically a gas. So, this is basically a solid which you need to deposit, and this is the substrate on which you want to make the deposit, and it has certain exposed part where this deposit will be made. So, this gas, as it travels, it encounters a temperature gradient. So, this gas gets again deposited, it goes back to the solid phase on the substrate in the locations that you want. So, this is commonly the thermal evaporation. So, if I repeat it once again, material to be deposited faces the target in a container. Here if I see on this figure, material to be deposited faces the target in the container. Target is the substrate on which you want to make the deposit. High temperature ensures sublimation of material. So, by heating you ensure the sublimation of material. Sublimation means going from solid phase to gas phase. Low pressure 10 to the power minus 8 torr, and I have already mentioned what 1 torr is. It is basically 1 millimeter of mercury pressure. So, 10 to the power minus 8 torr ensures avoidance of unwanted parasite deposition of molecules. That means, if in the gas phase there is unwanted material already present, that material also may get deposited on the substrate. So, by creating vacuum you ensure that only the sublimated material is present and only the sublimated material deposits it, there is no other parasite deposition. That means, sublimated material is getting deposited, by the side on the side of it some other material is also getting deposited. So, that you are trying to avoid. So, you are putting this whole system under vacuum. Deposit rate is typically angstrom per second. It is simple to implement and good for metal deposits. The other method that is there is called sputtering. Sputtering involves use of voltage and not heat. So, if a material which is heat sensitive, where you cannot apply lot of heat. So, there this sort of this technique is very useful. Here the target is on anode and the material to be deposited is on cathode. You remember what we saw last time? We had this physical vapor deposition, and how was it? We had an anode, we had a cathode, and we had placed the substrate on cathode, right? That was what the physical deposition, that is how the physical deposition works. So, you had anode and here you applied vacuum, and then you introduce a gas which get ionized here in the between these two electrodes, and then it bombarded the substrate to create the physical etching. So, that is what we have already studied. Here in this case you are keeping the target is on anode and the material to be deposited is on cathode. So, your target is on anode, this is the anode and this is the cathode. So, target is the substrate on which you want to make the deposit, target is on anode and the material to be deposited, that is on cathode. Use of cold plasma gives the option of depositing variety of material. So, you are creating a plasma inside. So, you do not need to rely on the temperature to get this deposition done. So, this allows deposition of variety of materials. Ionic kinetic energy of 0.3 kilo electron volt to 2 keV. This ensures penetration by 1 or 2 molecular layers of the substrate. So, this is not just the other layer is sitting on the substrate, it is penetrating, because you are applying a voltage, you are adding some amount of ballistic effect. So, it goes 1 or 2 molecular layer into the substrate. So, this is good for the adhesion. So, these are the two methods you have for physical vapor deposition. The next technique that I have here is chemical vapor deposition. This is a very popular technique, you might have heard of this technique. Here there could be either a homogeneous reaction taking place in the gas phase or a heterogeneous reaction that can take place at the surface of the target. Here you see the homogeneous reaction takes place in the gas phase and the product gets absorbed on the target surface. What I have written here is SiH4, okay. This is breaking down to silicon and hydrogen, okay. So, this silicon is, so if this is the substrate and you supply SiH4 which breaks down to Si plus 2H2. So, this Si gets deposited on the substrate and the hydrogen goes away. So, hydrogen goes away and silicon gets deposited on the substrate. So, SiH4 giving rise to Si plus 2H2, it gives rise to nucleation and growth of silicon crystal and desorption of 2H2. So, you do not have hydrogen, hydrogen is going back, and the silicon that is being deposited. So, after preparing the substrate, if you need to make a deposition of silicon at some place, that can be done by this technique. So, this is basically one form of chemical vapor deposition. All right. Similarly, it could be the heterogeneous reaction at the surface of the target. There the substrate itself contains the silicon, and oxygen comes there and reacts with this silicon to form silicon dioxide. 2 nanometer layer of SiO2 forms when silicon wafer is exposed to ambient air in any way, and the thickness of SiO2 will be 1 micrometer when exposed to air at 650 degree centigrade. So, that is the way it works. Now, this is an example of chemical vapor deposition which is of heterogeneous type. You are depositing SiO2 on the layer of silicon, on the silicon substrate. You want to cover one particular portion with SiO2. So, for that what you do is you encourage this, you ensure that you have this heterogeneous reaction takes place at the surface of the target at those selected positions. On the other hand, it could be that you want to deposit simply the silicon. In that case, you have SiH4 supplied there, and this SiH4 in the bulk phase it reacts with it reacts to form or it dissociates into silicon and hydrogen, and this silicon is deposited on the substrate. So, this is an example of homogeneous reaction. Now, gas phase diffusion ensures low defect density in crystal, that I already pointed out that gas phase diffusivity is much higher. So, it helps you in reaching all the places, and so mass transfer limitation. For example, a crystal formation requires that atom be supplied at the right time at the right place, then only a crystalline arrangement can grow in the form we said, 2 face centered cubic lattice separated by etcetera, etcetera. So, if we need to do that, you have to ensure that the silicon atom that we are talking about, that silicon atom is there when you want it in the right quantity. If you have a mass transfer limitation, one silicon could diffuse, but there was a concentration gradient, so silicon could not reach there. If such situation comes up, then it will not be straightforward. So, in that case the crystalline arrangement will be imperfect. You will not have exactly that 2 face centered cubic lattice interpenetrated in the way it is supposed to be. So, gas phase diffusion helps you so I mean you can do it otherwise, but there could be some defects you are introducing. Here the defect density would be less. Now, chemical vapor deposition is of 3 types. One is low pressure chemical vapor deposition, other is atmospheric pressure, and other is PECVD, plasma enhanced chemical vapor deposition. Okay, plasma enhances chemical reactions at the target surface using ionic bombardment. Plasma enhances chemical reactions at the target surface using ionic bombardment. Also, energy of incident particles helps penetrating into the target surface, resulting in constant film thickness and conformal deposition. What this means is, you basically what you need to do is you need to have a reaction, SiH4 dissociating into silicon and hydrogen, but you can provide the energy, through plasma. So, this plasma is enhancing the chemical reaction at the target surface, and also it is ensuring that the film thickness is constant and there is a conformal deposition. Conformal deposition means there is no hill and valley, the deposition is uniform, there is no ups and downs in the deposition. So, that conformal deposition can be ensured if you have this plasma deposition. So, reaction is conducted, the chemical reaction is conducted within the plasma chamber here. Low pressure ensures that the mean free path of molecules is high for easy diffusion of species. So, that is why this plasma enhanced, that is also at low pressure, and there is a LPCVD technique which is at low pressure. Deposition rate is of the order of micrometer per hour, and versatility in material deposited is there. This versatility in material to be deposited, that is there. This includes deposition of insulators as well. So, I mean, unlike physical vapor, unlike this thermal deposition for example, here this chemical vapor deposition, here you can have this versatility, and if you are using plasma enhanced plasma enhanced CVD, in that case you are ensuring that you have a conformal deposition. That means, the deposition that you make is uniform, it does not have hill or valley on the substrate. Now, I put it as if these are the two methods of deposition, this chemical vapor deposition and physical vapor deposition, but there is a third type of deposition which has already been there for some time and which you already know, which is called electrolytic deposition. Here the metal deposition on the substrate, which is held as anode, solution is metallic salt such as copper sulphate, metal ion, that is copper ion, migrates towards the anode. So, copper sulphate breaks down into Cu2 plus and SO4 double minus, right, and then Cu2 plus is attracted towards anode. Anode means it because Cu2 plus is positive, it migrates towards anode, where it gets 2 electrons and form the elemental copper, and this copper gets deposited on the electrode. So, metal ion captures electron at the electrode and form molecule that adsorbs onto the electrode. So, this is a very traditional method of making a deposition or making a coating. Electroplating you might have already seen. So, this kind of deposition you are already aware of. It is just that I mention it for I mean this should be a part of this exercise. This since we are talking about deposition, electrolytic deposition is very much there. Now, once you make I mean as I said that you have taken a substrate, you made channels, whether it is circular or in a zigzag manner or a straight line, you made a channel of certain depth. The depth, what depth you want, you can make it. Whether you want the wall to be vertical or whether you want the wall to be inclined, I mean that you have various choices. You can have you can go for wet deposition, you can go for dry etching processes. So, you have made a channel, you have carved channel on the substrate the way you want. Then on the channel wall, you maybe that requirement is that you have to put some electrode material at selected places or some catalyst material in selected places or some thermal insulation in some places. So, that deposition can be done using these methods that I discussed. So, once that is done, what you need to do is you need to put a lead on top of this on top of this substrate. You have made the substrate, made the channel, inside the channel wall you made the deposition, then you put a lead on the substrate and make it watertight. So, that it can hold some pressure. Okay. Then you consider this microstructure to be ready, and then you have to make some interconnects at selected places through which the sample can be introduced. Okay. And so, this microstructure should be ready. So, how to put the lead on that substrate, that is what we are concerned here, and what the title says is sealing in silicon and glass. What I write here is grooves carved, this should be I think CARVED, grooves carved, this is carved. So, CARVED, grooves carved onto the silicon wafer must be covered with another glass wafer in watertight manner to complete the making of device. Now, anodic bonding, there are ways to do this. One is called anodic bonding. Okay, there are methods to do it. One is called anodic bonding and the other is called fusion bonding. By these methods you can bond you can bond a silicon substrate, you can put a lead on top of this. Now, anodic bonding refers to glass silicon sealing by the use of intense electric field 1 kilovolt and elevated temperature 400 degree centigrade. The way it works here is that suppose this is the silicon wafer, the silicon substrate on which you are putting another lead. So, this is made of silicon and this is made of glass, all right. So, you are applying a voltage across this. So, how do you apply a voltage? You put this you apply voltage across these two. So, this is one is glass and the other is silicon. Why are we sealing it? Let me put it this way. Suppose this is the substrate, this is the silicon substrate on which you have carved a channel. You have carved a channel here, on this you carved a channel. So, how does the channel looks like? So, you have carved a channel here, you understand, and on top of that you are putting another lead. This is a solid one. So, this is the second one you are putting it on top. So, that this channel was otherwise when you have done the etching, you have done this part, either this or at an angle. Now, you have to cover this, right, then only the channel will be complete. So, that is exactly what you are doing here. That is exactly what you are doing here. The bottom one is silicon that has some channels at some place, okay, and on top of that you are putting the another glass slide of similar dimension, and then you have to bond. Bond means these portions, this glass and silicon, this has to be watertight. So, that if you make a port here and through this you introduce the sample or apply some pressure, okay, and you have another port for some other reason. So, when you put some liquid there, liquid will flow through the channel, this becomes watertight, this should not come out and start leaking from here or start leaking from there. Got my point. So, that is the purpose of putting the cover. So, when you put the cover, you have this silicon, on top of that you have this glass layer and you are applying a voltage. That is what we are talking about here. Anodic bonding refers to glass silicon sealing by use of intense electric field 1 kilovolt and elevated temperature of 400 degree centigrade. So, not only you are applying a voltage, you are applying heat as well. The value is 400 degree centigrade. The electric field induces migration of sodium ion Na plus ions in the glass to the interface and interpenetration of atoms at the glass silicon interface. You understand what a glass is, you understand the composition of glass. You might have already seen it has sodium ion, and other than that you have orthoboro, heard of this? Orthoborosilicate. And so, you have a sodium ion and you have sodium as a positive ion in that glass. So, when you apply this intense electric field, this sodium ion goes to the interface and it goes for an so there is you are ensuring interpenetration of atoms at the glass silicon interface. So, that interpenetration is and at the same time you are applying a temperature of 400 degree centigrade. So, that interpenetration is basically creating the addition that you require here, and these are very perfect addition. Now, one issue here is that since you are having silicon and glass, this thermal expansion coefficient of silicon and glass could be different, and when you take this to 400 degree centigrade, if the thermal expansion coefficients they are not similar or not of similar order, you would expect crack, bending and all these things taking place, because on one hand it tries to expand to the two one silicon substrate and the glass lead, they try to expand by different magnitude, that is one issue, and at the same time you are trying to bond them. So, you will develop crack. So, you have to ensure that the glass lead that you choose, that has thermal expansion coefficient similar to silicon. That is the fourth point that I have on the slide. Thermal expansion coefficient of glass lead should be same as silicon to avoid crack, and this is a Pyrex Corning 7740. This is one basically a commercial product which is suggested for this purpose. This is the type of the glasses of glass can be of various types, and this is the type of glass that they have chosen. That can be suggested, that has been suggested in literature. Now, this anodic bonding, this cleanliness of surface is extremely important. If the surface, if the in between silicon and glass layer, if there is a dust particle, that can go against this sealing process. So, cleanliness of surface is important, and for that probably you have to clean it. We have already discussed about some protocol. You dip it in acetone and dip it in alcohol and dehydrate and all this. So, but the purpose here is that there is not any such substance, and the operations are to be done ensuring that the ppm level of particles of certain diameter is less than a limiting value. So, these are few things which you ensure to these are a few things which you look into for ensuring this cleanliness of surface. Now, anodic bonding between silicon to silicon is possible. We talked about a silicon substrate and on which you are putting a glass lead. Now, you may say, if I want to put a silicon lead itself instead of glass, okay, that is highly possible. The only thing is, then there would be an intermediate glass layer, because this aspect of sodium ion dangling and going into the silicon phase and forming an interpenetrating network, that is possible between silicon and glass. So, to utilize this, what you are doing is you are putting a very thin layer of glass between two silicon. So, one half of the glass connects with the upper silicon lead and the other part of the glass connects to the lower one, the silicon substrate, and that is how you can have a bonding done. So, what you do here is anodic bonding between silicon to silicon is possible through intermediate glass layer. So, you put an intermediate glass layer just for the bonding purpose and nothing else. Thin glass layer of 0.5 micrometer to 4 micrometer, a thin glass layer can be deposited on silicon. Now, the question is, how will you deposit this on the silicon? I have a, suppose a silicon substrate is there, plain substrate. I want to make a coating of 0.5 micrometer to 4 micrometer. Again, this deposition can be done on silicon by physical vapor deposition that we discussed just now, or spin on technique. So, you have a glass melt put there and then you spin it and you form a layer. So, there are methods to do this. You should appreciate, because you have been introduced to these ideas. Now, seal from anodic bonding is watertight up to 100 atmosphere. That is a very high value, it looks like. Now, fusion bonding, which is the other type of bonding. You remember at the very outset I said there are two types of bonding possible. One is anodic bonding, another is fusion bonding. Now, fusion bonding refers to bonding between silicon and glass as before. Only thing is that entire penetration of Na plus etc., these are probably caused by not by application of any voltage, instead the temperature or the heat takes care of it completely. So, the heating is instead of applying any voltage, the heating is to be done, and the heating has to be to a very high temperature, 600 degree centigrade to 1100 degree centigrade. So, if you can take this silicon and glass silicon substrate with the glass lead, and if you take this to that temperature, you can expect a fusion bonding to take place. However, anodic bonding is more popular. Anodic bonder is a device which is available for people who are working with these microstructured fabrication. Now, so far what we discussed is that I said at the very outset, this photolithography, etching and all these things, these are concerning only the silicon substrate, silicon or glass. I said you will have, when it comes to weight etching, we discussed about anisotropic etching, and then we said that the same thing will have isotropic etching in glass, but we restricted our discussion to silicon and glass. But there is a huge there is a major part of work which is there, not with silicon and glass, but with plastic material. And at the very beginning we discussed about this. We mentioned that plastic materials, in fact, if we go back to the previous slide, what we see here is that there is plastic MEMS, okay, and there we what we mentioned at that time, that the range is 0.5 micrometer to 500 micrometer elastomers such as PDMS or PMMA. These are used. The channel can be made by either direct method, by laser ablation, or replication method by use of mold. Okay. Now, mold is basically a negative replica. You understand what a negative replica is, that the negative, suppose you want to make a channel. So, in the mold you will see a raised portion there, and then when you pour a liquid, pour a polymeric liquid on this and let the polymer to solidify, then when you peel it off you see the positive one, the channel engraved in that. Okay. So, that is the use of mold, and the laser ablation is that you take this plastic material and selectively remove some material by application of laser. Or there are other methods, there are other direct methods also available. We will discuss this briefly later. By weight plastics are 100 times less expensive than silicon. So, and can be made disposable. So, this is the benefit of plastics, use of plastics, and rapid prototyping is possible, because if you are using replication method, then you need only one master, and on that master you put something, peel it off, put another one, use the same master. So, you can do the replication over and over. So, these are some of the benefits you have. Also, the other benefits are surface effects. You can induce surface effects on polymeric material very easily. You can make a surface hydrophilic, you can make a surface hydrophobic, you can make that surface attracting to some other material which is flowing. So, you can make it, you can introduce these surface effects. And transparency, if this plastic material can be very much transparent. Okay. So, you can see from outside through which the liquid is flowing, or more importantly, if the optical element, if a part of the optical element you want to keep it outside, okay, if it is optically transparent, then still you can expect the light to of certain wavelength can pass through this material, and diversity of materials can be introduced easily. So, these are some of the benefits you have. Of course, there are some strong disadvantages. One is, say, aging, because plastic material, if you leave it for some time, it may, the properties may change and it may buckle. I mean, if you have a channel of high aspect ratio, you remember in the last class we are discussing about deep reactive ion etching, where you can make a channel or make a hole which has high aspect ratio, diameter is of the order of 10 micron and the depth is 500 micron. There, if you make a channel of such dimension in plastic material, this material can bend, can buckle. So, channel may not retain its dimensions uniformly. So, these are some of the benefits we had at that time. So, this is a plastic MEMS device which is another branch of material, I mean, which we did not discuss. We have been focusing so far on silicon and glass. Now, there is a reason for doing this exercise for this plastic for making this plastic MEMS as well, because to make that master, I said you have to create the negative of it and use that to replicate the positive ones, right. Now, how will you make that negative one? So, it could be that the silicon substrate that you make, that itself acts as the mold. Got my point? The photolithography technique is used to make the mold. The mold is not made of metal, I mean, which commonly we thought the mold will be a metal on which you pour the polymer, but mold could be silicon itself, and you can make the negative, make that mold using photolithography technique. So, that is the so you cannot. So, if somebody says that okay, I am only interested in plastic MEMS and I do not care what happens in photolithography or what happens in say silicon and glass and how you bond, anodic bonding or fusion bonding, because after all plastic, when you have a plastic device and on top of that you put another plastic lead, okay, and then when you try to bond them, definitely anodic bonding will not work, fusion bonding will not work. So, why are we getting into this if I am only concerned with plastic devices? First of all, there are disadvantages for which you need to resort to this silicon device, and secondly the mold has to be made first, and that mold, for making the mold, photolithography technique is used. Okay. So, if I go back to my new slide now, so we are talking about fabrication of plastic microfluidic devices. Now, there are 3 common methods. There are other non-traditional methods also available, but when it comes to traditional or methods that are commonly used is molding, casting and micro injection. Okay. Now, I am spelling it out as MOULD, but that is a perfectly that is the old traditional spelling. Now, mold is the negative master made of silicon, electro deposited metal or reticulated polymer. So, this is a mold. So, mold is basically the negative master. The master is that one which remains there, and using the master you create thousands of replica. Okay. So, here the negative master can be made of silicon itself, or it could be electro deposited metal, or it could be reticulated polymer. Now, common method of making a mold is photolithography. If it is silicon, then you will use photolithography to create, of course, not to create a channel. You have to create a channel, you have to create a raised face. So, probably you have to go for a vapor deposition to create that raised face. Okay, mask the rest of the material, rest of the part out and go for a vapor deposition. Or if you want to eat away, or if you want to do the etching, you have to do the etching for rest of the part. Channel means if you etch out a portion other than that slit, then you get a raised face. So, there are various ways you can do it. For processing at high temperature and pressure, electro deposited or traditional micro machined metallic molds are used. If the processing requires high temperature and pressure and on an industrial scale over and over again, then probably one would go for a metallic mold. And how do you make a suppose an extra layer? Then you have to go for an electro deposition. We have already talked about the 3 methods of deposition, right? Physical vapor deposition, chemical vapor deposition and electrolytic deposition. So, electro deposited or traditionally micro machined metallic molds can be used when the processing is done at high temperature or pressure. Now, this process, first of all, I said there are 3 methods, right. So, we mentioned in the previous slide, we mentioned 3 methods. One is molding, the other is molding, casting, and the third one is micro injection. So, these are the 3 methods we are talking about. So, now, if we focus on this first one, the molding, that is what we have in the next slide. Catalyst plus polymer is poured on a mold and heated. Catalyst plus polymer is poured on a mold and heated. So, you first of all you take this polymer to a molten state. So, it is like a liquid, and you take it, suppose this is the mold. Suppose this is the mold. Okay. Now, you take this, suppose you take this molten polymer and pour it on this mold. So, this is basically the mold. On this molten polymer is poured. So, what will happen is you will form a layer like this. Okay. you heat the mold as well, so that if there is a tendency to for the polymer to solidify here in the corners, you will ensure that the polymer flows everywhere to all the corners, okay, and it forms a layer. Okay. Then you later the structure is peeled off the mold and contains the pattern of the mold in negative form. So, when you peel it off, how will it look? The upper portion, if you peel it off, this would be the upper portion that you peel off. When you peel off and the mold is ready to be used again, and again you put next lot and again peel off. So, you will be creating these structures. That is what molding is about. Now, the common polymer is PDMS. I said at the very outset there are two polymers, one is PDMS, other is PMMA. Okay. PDMS has this will melt at a temperature of about 70 degree centigrade. It is, you can see that temperature of about 70 degree centigrade is required. So, you have to heat this polymer to 70 degree centigrade, so that it melts. Now, the other polymer, which is PMMA, you will find that the temperature at which these we will operate, that PMMA material is used for casting, there even it is 120 degree centigrade, PMMA will not melt. Okay. So, PDMS will melt at 70 degree centigrade, and this PDMS material is used for molding, but this PMMA material, polymethyl methacrylate, that is not used for molding. As such, that PMMA material will not melt even at 120 degree centigrade. So, that you have to make note of the type of polymer used here as well. Okay. The other method, the second method, we had three methods we talked about, right. One was molding, we just now we stated, and we said this PDMS is a common polymeric material which melts at which is liquid at 70 degree centigrade, which can be used for molding. The other method is casting, right. Casting is basically this is done with PMMA, and you can see the fifth point here in this slide. Temperature is about 170 degree centigrade and the pressure is 10 to 100 bar. Okay. So, what you do here is, here you do not get a melt and you are not going to pour this on the surface. Rather, what you do is you will put a stamp. I mean, it would be in a common casting method. I mean, if you look at a just conventional casting, not a micro scale casting, it is like this. You have a sheet. I am talking about conventional casting, not micro scale casting. You have a roller here which has teeth like this. Like this, and this roller rotates. Here you have another roller, this roller also rotates. So, this plastic material goes out and this whole assembly is heated. This whole assembly is this material, this place is heated, this place is heated. So, what you are doing is basically by application of heat, the polymer, this is basically a plastic layer, and this remains solid. This is not like it is being poured from a jug. It remains solid, and but this becomes deformable by application of heat. Otherwise, it was a solid and you cannot create a dent on it, but by application of 170 degree centigrade, you are ensuring that the material is deformable, it becomes soft. And now you put this stamp, this is called I mean, here we have just a tooth here which is creating a channel on this film, on this layer. So, you will be having when you get this, suppose this is a roller which has a dimension here, okay, and this also has a dimension here. So, the plate that you will get, so you would be generating something out from here, and after you will be getting channels like this because of this heating deformation and at the same time applying a stamp, applying a mold. Okay. So, here the mold or stamp is pressed into a heated deformable material. After cooling and separation, the structure represents negative of mold. These are what I am discussing is a very traditional casting process, and this is on a continuous basis. Okay, but what I am talking about in the slide there, here it is a more of a batch process. There probably you put a you take the entire thing in a chamber, put the polymer layer, then you heat it, so you apply heating layer outside, so that this is heated to 170 degree centigrade. Bring in the stamp. Stamp means you have this, no, it should be the other way. Bring in the stamp and then you push it hard. So, once you push it hard, this is molten. So, you will be creating a dent. So, what you would be producing is like this. So, this layer will take this kind of shape after it is done. So, the one that I am talking about in the slide, it is basically a batch process. After cooling and separation. So, when you take this off, take off this mold, then you get the layer in which you have the impression. So, the structure represents negative of mold. Common polymeric material is PMMA, the other plastics PVC, PIC, P, these are all this could be common polymeric materials. This also goes by the name hot embossing. So, basically you are heating the layer so that it becomes softened, and then you have a stamp which you are putting so that you form an impression, and that becomes the channel. So, that becomes the channel. Here this becomes the channel. All right. The next topic that I have here, which goes by the name micro injection, and this is meant for serial production on industrial scale. Here it is basically a molding process. It is basically a molding process, but not like this, because this is not this method that we discussed here. This method that we discussed here, this is not a good practice when it comes to serial production on industrial scale. So, on industrial scale, the injection molding that is commonly used for polymeric materials, that method is borrowed to generate on a continuous basis on serial production of micro scale device. What you do in this case is you have a hopper, okay, and you have a screw by which you are pushing this polymeric material, and you have heating arrangement, and by which you are pushing the polymeric liquid into this, and now here you have this polymer comes out like this, and here you have the other part. Okay, now suppose you have this like this. All right. So, this is a jig which is sitting there, and you are pushing the molten polymer through this. So, molten polymer is put through this hopper, and using this screw conveyor you are pushing the molten polymer through this port, and this jig, it comes here once, get fitted to this, and then it moves out. It gets fitted to this and moves out. It has a movement like this. All right. On top of this, one possibility could be that you can have some vacuum arrangement, which would be possible. This vacuum will ensure that liquid reaches all the corners, all the nook and cranny of this this mold. So, what you have here is, suppose it comes there and silts to this. Suppose there is a arrangement which pushes this one and it silts. So, you have a layer being formed. You will form a polymer layer like this. Next moment this whole assembly goes out, moves out, and this layer comes here. This layer, just a thin layer with the appropriate channels in place, that comes down. That simply fall. That is just a fall. That simply comes out. It peels off, and it is falling down. Again, this block goes back, fits to this jig. The next layer is formed, and then you collect another one. Then you collect another one. So, this would be a serial production. So, basically what you are having is, you are having this jig which is moving back and forth, and continuously polymer is supplied through this hopper. So, continuously you are supplying the polymer, continuously this is, I mean, of course, it is arranged that way. The time it takes to come back, time it stays there, and time it goes back, that is sufficient for this polymer to spread through the places, and this you get a perfect device. So, this is ideally suited. I mean, instead of going for a mold where you take it in a jug and pour it on the mold and then wait for this, remove it, this is more of an automated system by which you can create hundreds of them in a very short time. So, this is the common, this is a replication method which can be used on an industrial scale. This can be used, this molding method that I am talking about, this can be used on a lab scale or on a small scale. This is good for serial production on industrial scale. Now, injection molding, I suggest, if you want to look into, because this picture may not be as perfect, you there are various pictures that should be available of injection molding, not micro injection molding. Basically, injection molding is the idea that is taken, and injection molding is very similar. Okay, but injection molding is definitely not in micro scale, but here the idea is taken from there. So, if you want to know further about this process, you should read about injection molding. There should be very established literature available, and this injection molding, this idea is taken. Now, you have to tailor this. I mean, I am just introducing these techniques to you. These molding and casting, these are very traditional method used for polymer, used with polymer sheets. Okay. So, these are anybody who is working with polymer composites, they should be aware of these techniques. Only thing is, since people are making plastic MEMS device, so they said, okay, these techniques we should borrow from them, but they have to be tailored to, so that it suits the purpose of making micro scale devices. So, if I quickly go through the slide, what it says is, it is meant for serial production on industrial scale. The liquid plastic material is injected into a mold under a vacuum at a temperature greater than glass transition temperature. Okay. Under a vacuum means you apply, put a line of vacuum and it connect it to a vacuum pump. The idea of a vacuum is that, so that, because if air remains trapped, I mean, think of it, that liquid is flowing and in certain portion the air remains trapped. So, if air remains trapped, then the material that you get here, here a bubble of air sitting there. So, that will not serve the purpose. So, you have to have a vacuum line so that the air will be sucked out. So, you will get liquid, you will get polymeric melt, that moving that goes to every corner of that mold. That is very important. Okay. So, that is greater than, and it has to be greater than the glass transition temperature. Okay. Next, the system is cooled down below the glass transition temperature, and the mold is taken off, and a structure corresponding to the negative of the mold is obtained. That is exactly what you are doing. So, this whole process, taking it just above glass transition temperature and cooling it down, and then removing the mold, the entire process is automated. So, this is good for serial production. So, this is what we have as far as plastic MEMS device is concerned. There are other methods, I will discuss them briefly, and then we talk about then we talk about the plastic device, how it is these plastic devices, they also have to be bonded. If you have a plastic substrate and on top of that you have to put another plastic substrate and bond it. And finally, once we are done with this, then we will discuss about the interconnects, how you make a port and how you can put a tube through that, and that part I have not discussed for silicon substrate. So, we will that part is left out. So, that would be a general discussion. We discuss about how to put a tube in a silicon micro device or how to put a tube in a plastic device. So, once we do that, I think our microfabrication the discussion on microfabrication will be over, and then we will go into the theoretical aspects of microfluidic device. So, I will take probably another 2 classes or so to wrap up this microfabrication, 2 or 3 classes maybe to wrap up the microfabrication, and then we will go to the actual how the various aspects of transport phenomena getting affected because of this micro scale effects, and we will go from there. That is all I had for today's class.